Hello, everyone, and welcome to our plastic injection molding parts clinic, featuring our speakers, John Sidorowitz, our Director of Operations, and Glenn Miller, tooling engineer. John has been with Eccentric over 10 years, is a technically minded sales leader and problem solver in all things manufacturing. Having a degree in management and a very diverse background, John understands the entire manufacturing process from design to final product and everything in between. Glenn has worked at Eccentric for almost 3 years as a tooling engineer and quality control specialist. Prior to joining Eccentric, Glenn spent time as a CAD tool designer and tooling engineer with over 25 years in injection molding. This presentation is expected to last approximately 45 minutes. There will be a Q&A session at the end of the presentation, but you can use the questions field on your screen to ask questions during the presentation, and we will address these throughout the webinar. So if you have questions about any of the parts or the molds as the guys are going through them, please ask them at that time, and we will get to them throughout the presentation. We encourage you to follow Eccentric Mold and Engineering on LinkedIn so that you can stay up to date on our latest blog topics and webinar schedules. So I'll now turn over the webinar to our experts, John and Glenn. Gentlemen.
Thank you, Mark.
Thank you, Mark.
Thank you, everyone, for joining this afternoon. Once again, this is going to be a very interactive webinar. So we're going to kind of go through some parts. Let me get the agenda up here. So what we're going to do, I think there's about 7 parts total. Hopefully we can get through them all, but depending on questions, we might be able to get through most of them. So what we're going to do is kind of display the part, kind of talk about the part a little bit, how it's used in its functionality, some of the challenges that we encountered, if any, point out some key features, and then review any of the questions that you guys may have in regards to part design, tool design, or anything just related to the whole process of developing that part and tool, and then just kind of repeat through the rest of the parts here. So with that, let's get started. So this part, it's a small, intricate part. As you can see, we've got a lot of clip features or snap features around the part, around the inside perimeter, as well as this little slot feature with internal clips. So as you can imagine, there's a lot of action going on in this part. This is a kind of a half to a housing, and we ended up going with manual actions. This wasn't a fully automated tool, just due to the low volume nature of it. So we ended up with loose pieces or hand picks or hand loads, as we call them. So I'm going to pull up the tool design and kind of show you how we ended up designing the tool to eventually get the part that the customer needed, because it is a pretty intricate part, especially when you get into this little round section here. Just make sure we can see my screen here. That is definitely not the part. That is a new. All right, so here we have the part. Let me just change the transparency of this part here so you can kind of see what's going on internally. And I'll shut this off because it's not really needed at this time. So as you can see, we've got, the 3 clips kind of on the outside of the part. These are all loose pieces to capture these undercuts. The real challenge with this part was, this section here. So it ended up being broken up into 2 sections, really. Well, 3 total parts if you're looking at it. So we had one hand load that would come out, and then that would free up this other one to allow us to capture these clip features. Let me put all that back so you can kind of see how that all goes in there. There is another loose piece that was here. I don't have that highlighted, but yeah, so in turn, we ended up with 4, 5, 6 loose pieces to create this small part. So this is, a little bit more on the complex side, but
yeah, I mean, you can see where we have those undercut features on the clips, and obviously that won't pull free from the tool. As John said, in this particular case on this tooling, It's more of a prototype, so we went with hand loads. That type of feature could also be formed with lifters. And as he said, with that round feature at the end, that's pretty intricate with those clips facing inward. It's a die-lock situation. If we were trying to pull that in one direction out, that's why we had to split that so that we could capture part of the tip of the clip in the magenta hand load, and then the rest of that feature pulls out the other direction to get the bottom of it. So there's quite a bit going on there, and it's a very tight area. It was a challenge, but and parts ended up looking really good.
Yep.
So guys, we have a question. Someone has asked, what is the overall size of this part?
This part was roughly, I want to say about 2.5 inches long on its longest here.
Yeah, kind of about the size of one of those old pagers. You know, it's a kind of that type of feature.
Okay, and then another person has asked, when you say loose pieces, how are those pieces located and placed?
So let me turn this on so you can kind of see if I shut the part off here. Oops, didn't want to do that. I wanted. So you can see the, oops.
So basically you've got that core steel where the blue's highlighted, and then you can see the outline of the hand load. The hand load's actually finishing off that core side. And then when the part ejects, those hand load pieces come out with the part. So there would be ejector pins down underneath of that hand load. Sometimes those are free, and sometimes we have a hole that locates those on the ejector pin. So when the ejection system pushes forward, those hand loads pop out with the part, and then the operator has to go in and manually pull those off inward to not distort the clip and damage anything.
So here's kind of a section view of that loose piece that creates that clip feature. So the red is loose. Gray is going to be stationary on the core side. So the material will fill in, create the clip feature, then this red piece will come out with the part, then manually remove from the part, then insert it back in the tool and just repeat.
A tool like this with hand loads that are manual, this kind of tool needs an operator. We wouldn't be able to run this tool overnight, which is a term we use, automatic overnight, which would be a part that mold that runs automatically with actuated pulls and so forth. So adds a little bit to the timing and how long our part runs would take, since we can't run it without an operator in place.
Okay.
Another question related to this part. Are there any issues with flash between the loose pieces and the rest of the mold?
I mean, there will be witness. It's almost like a parting line. So there'll be witness on the inside of the part where you'll see the outline of this loose piece.
And if we do run into as this mold runs, things will wear. We start seeing heavier seams. We'll go back in and we can tighten those right back up and sharpen up all the parting lines and get that back to normal. It's preventative. We can do preventative maintenance on tools, but then also we can always go back in, rework these pieces and refit them to the tool and respot them to maintain some clean seams. But as John said, there's always going to be a witness line from those hand loads.
Right.
And then, John, you had commented about the hand loads, and I think Glenn, you mentioned that this is something that we couldn't run overnight. It wasn't automated. But someone has asked the question: can the loose pieces be loaded and removed by the use of robotics?
They could be. Obviously that would be a much more sophisticated setup. Probably multiple robots coming in. The cycle time would probably be a little longer. As you can imagine, having all that happen within the open and close of the tool, the expense of the tool, there's quite a bit more involved to try to make that more of an automated process. that was a concern. We could automate in certain situations like this, depending on the clearance we have. We could automate those to be lifters. The bigger challenge is the circular area with those clips in there. That's something that we'd have to do manually regardless. I hope that answered the question.
Okay. All right, we'll flip back to the PowerPoint now. So that was part one. So our second part here, it's we had to work with this customer on coring this out. So you can see some cored out sections here, just due to material thickness. We had some sealing surfaces. We've got some internal threads, and there's actually a pretty, I wouldn't say complex, but a locking feature on the other end for what, the other end, or this end that mates to another part. So we've got multiple actions on this one, similar to the previous one. So let me pull that one up.
And when John's talking about coring out, we're simply trying to get as nominal of a part thickness throughout, not have any super thick sections. Thick sections tend to wreak havoc on sink and the fill and possibly dimensionally. So anytime we will with the customer and suggest removing some material if possible for more of a uniform part.
So in this design, the customer needed a higher volume than, it's probably 2,000 plus pieces a year. So we automated a portion of the tool. So we can see our slide and everything on the left here. To create the other end that had the threads, in a production setting, you typically have, unscrewing cores, but the budget didn't allow. So we kind of did a 50-50 split. So part automated, part manual, just to ease the running. So I can start shutting this off so you can kind of see. I don't know if that's really gonna go, but let me just shut this off.
So you've got a piece in the end there that the slide actually pilots into to form all of those features in there. Yep. On one end with the horn pin there. And as John said, the other side of it is a manual hand load that's unscrewed, and that can be done with actuation, with hydraulics, with some other form of unscrewing mechanism. But as we said, sometimes the budget doesn't allow for certain things in the tooling. So we do what we can to automate as much as possible, and that's for the customer, and it's also for our team on the molding floor as well.
So just you can kind of see this section view. We've got, essentially one loose piece or hand load embedded into another, just due to the part design. So we've got this small channel or groove that runs around that is for a seal. So what happens when this tool runs, part comes out, these two, the teal and orange, come out with the part. The teal part is removed first, and then the orange part is unscrewed from the actual part. And then again, it just gets all loaded in, tool closes, left-hand side, this closes back up, pushes back in, shuts off on this surface here, and we end up with our part.
So John, we've got a couple of questions. I think the first one actually goes back to the last part, but you don't have to jump back to there. The question is, when designing various snap fits, do you reference any engineering spec for tolerances and sizing of the clip and mating surface?
I mean, that's going to be, it's going to really depend on the design. Is it made to come off? Is it going to be frequently pulled on and off, or semi-permanent, or one snap and done? So it's hard to answer that.
Yeah, I mean, many times we don't have the full picture. We don't have the full assembly to really understand the nature of what the customer is going to use this for. Like John said, is it a snap and a permanent, or is that clip required to pop in and out? It really depends on the specifics of the assembly itself.
Yep.
Okay. And then with regard to this, and you had mentioned that this is partially automated. The question is, what is the benefit of partially automating a process like this? Can you run overnight and unscrew the hand load pieces the next day?
No, I mean, we only have, on some tools, we may have 2 or 3 sets of the hand loads, especially for this feature, but it would not be able to run overnight. Basically, you'd get one part and then be done. We'd have to have something manually put in there. There's really no way to automate it other than redesigning the entire tool with mechanical actuation, hydraulics, or some other form of pull.
And I think that you guys mentioned early on that this was partially automated to reduce cycle time, but the budget didn't allow for full automation. So yes, that's the benefit of this, right? Is that it helps to reduce cycle time within budget constraints.
Right, and we're also adding that slide on the end. It's beneficial to our molding team as well. That's one less hand load that they have to handle and put in and out. It will help with the cycle overall. They still have to do the one end plus some of the internals, but that one slide on the end is helping with shortening up the cycle time a little bit and taking a little out of the hands of the molder.
Okay. Next question, can you just make it multi-core for each shot and then allow for manual work to have another relaxed timing?
I'm not sure what that question's asking, to be honest.
Maybe multi-cavity.
I mean, a tool can definitely be multiple cavities if required. We can definitely do that. It'd be a bigger tool. It'd be more expensive, obviously, going to a different press, but multiple cavities generally we can do depending on the part shape and the space we have.
Yeah, and multi-cavity, I mean, moving this to a 4-cavity doesn't always mean a faster cycle time. In some cases, it may be better to have a 2-cavity tool with 2 or 3 sets of hand loads or loose pieces. That's going to allow you to, I think that's what you might be getting at. It'll allow you to, get the cycle down, and then while the next part is being shot, you can remove those loose pieces from the part, so the tool isn't waiting for those loose pieces to be put back in. So that's one way to improve cycle. Obviously, automating it completely is the fastest, but your tooling is going to be much higher. You're going to be looking at those types of tools if you're dealing with, 5,000 plus pieces a year. When you're dealing with a few hundred, typically the manual is the way you want to go.
All right, so guys, the person who asked the question did come back with a little clarification. Multi-cavity, in parentheses, automated, then unscrew manual in better, more controlled time that will not affect the resin. But then later on, you guys, I think it looks like you guys answered it. So you said, yes, that's right. Got another question.
It would be multiple hand loads would be created so that, as John said, we can pull this out. The part can be demolded separately while another hand load's being put into the tool to kind of minimize the gap there and the resonance in the material with the barrel. There's all sorts of things that you don't want to happen. So yes, multiple hand loads would assist in speeding up the cycle.
Okay. Next question is, can the blue block that forms the seal be a slide action also?
It could. It's just going to get a little bit complex in here. I mean, it's such an easy, we're already, pulling that section of the tool out. It's going to make a much bigger tool. So if I, so you can see, within this mold base, we're pretty tight. To add something like this to this end, it's going to make a much bigger mold base, which means a more expensive tool.
Right. I mean, you're going to have a slide that would pull out. The operator still has to reach in there and get that hand load feature out of the part. So yeah, I mean, your tool size is probably going to increase by 50% at least, just to have room in there for that kind of actuation.
Next question, while you're removing the insert, how do you make sure you do not overcook the plastic that is awaiting the next shot?
that goes back to potentially, depending on the material used, the question is a good one. The longer that stuff sits in the barrel, it kind of cooks. It can really degrade the material itself and cause issues. So again, multiple hand loads would help decrease that amount of time significantly. So again, as John said, it depends on how many parts per year you're looking at. If we're talking about a few dozen, a couple hundred, we're probably good with one, maybe two hand loads. But if we wanted to, we could make any number of hand loads to speed that up.
Right.
Next question.
I just one more thing. Since that's a thread, a lot of times the hold time on that is critical just to maintain the accuracy of the threads themselves. So those little threaded pieces could also be used sort of as a holding fixture, as it were, to kind of maintain that size of those threads.
Great segue, Glenn, because the next question is about the threads. Is there any way to design the internal threads so that you won't need a hand-loaded part?
Yes, but again, it's all about the engagement to what it's screwing onto or attaching to. So they can be really shallow and be strippable, and you're kind of limited on material as well. So you got to think in reverse. If it's easy to pop off the tool, it's going to be easy to pop off whatever it's attaching to.
Right.
So if it's just a not a super tight engagement that's needed, then that could be possible. But if it needs to be a nice, tight grip and tight thread, then this is the way you'd have to go, or in a production setting like unscrewing cores, where it's automated and will unscrew itself.
Right. If that was a different material, something with a little more rubber content, if it wasn't a thread, perhaps just a gasket seal, perhaps that would pull free and pop out and go back to shape. It really comes down to the each individual component and the material being used.
Okay. All right, let me flip back to head on to the next part here. So this is a pretty unique part. It's got clip features again. It's actually not terribly difficult, but there are a few ways that you can build it, and we'll kind of get into that tool here now. This is part 3. So I really don't need this. So kind of what we did we almost built a tool within a tool, just due to the gating and how the customer wanted the gate and budget. So you can see, this is the core, and then we have basically a sub core and cavity in here. But our runner system runs through, this hole down and feeds through this into the side of the part here as an edge gate. So I'm going to shut this off here so you can get a better idea. So it's 2 halves. So it's two actions. It doesn't need to be there. We've got a couple core pins that, this core pin that are creating these tall posts. The clip features are being created by, the 2 hand loads on each side. So this part's going to have, 2 parting lines, one through the center of the part between these 2 hand loads, and then one along this bottom edge here. So you can kind of see this would be the parting line along this orange line here. We've got some internal ribbing, to give it some structure from warping and collapsing, on the side walls. Now the customer, I believe, if I remember correctly, in a normal situation, you'd kind of build this laying down, use your core and cavity, slide, coming off this side, hot runner or hot drop, dropping on this section of the part. We were trying to mimic their production tool in the gate location, which is why we had to kind of do a mold within a mold. if there's any questions on that one.
They don't appear to be.
Okay, this one was pretty straightforward, but it was just unique in the sense it was a mold within a mold. Let me go back here. So this next part, it was a highly cosmetic part. So it consists of a substrate and overmold. The gray is the substrate or a two-shot. The green is the overmold, which was a TPE, rubber, and it had to look good. It was prototype kind of bridge parts to production. Had to have nice, clean, tight shutoffs around the part, no flashing, and I'll show you how we did it. So I'll shut the block off here. So it's similar in the sense of, this is the substrate. Let me get rid of that. That is the overmold. Let me do this. All right. So essentially, most of the part is created by two hand loads, at least the sides. We've got a core section here. I just kind of make this transparent so you can kind of see what's going on internally. So we have a core inside here, two hand loads creating the pockets that are eventually going to take the overmold material, groove in the back here. Once again, we have two kind of main parting lines running along this edge here and then along the bottom here. I mean, this part is pretty straightforward.
I mean, really the most critical part of any kind of substrate overmold situation is the substrate fit into the overmold itself, where we're going to be putting in that green, that center material. It has to be tight, perfect. Otherwise, you're going to see flash seeping around those edges, and you can't have that. This is functional, and it also has a logo feature on there. It's cosmetic. It has to look perfect. So maintaining those shutoffs and running the substrate tool consistently with the same parameters, so we're not shrinking it differently, causing other issues, because that'll cause flash. It's the process itself is it's very tight and hard to maintain, but the part ultimately comes out looking really clean and really nice.
Mm-hmm.
So guys, we've got a couple questions about this part. First one is, how do you ensure that the overmold stays on the part for the life of the part?
Well, that's really going to come down to material selection. What your substrate and overmold. There's a lot of overmold materials, like TPEs, TPUs that are made to work with, say, ABSs or polycarbonates or nylons, specific to that, where you get a good chemical bond. When doing overmolds, you want to, promote chemical bonds as well as mechanical holds. Typically doing pass-throughs, like holes through here where the material just locks into the part. In this case, it was more a chemical bond. We have a lot of surface area that's getting filled in by that material. So that's just gonna keep those two basically materials together.
I mean, that you can see that overmold material wraps around the substrate through to the other side. So all of those features will help hold that in place and keep that adhesion to the substrate.
So you can see the inside here, some of the overmold, which is the green section, kind of passes through, but most of your adhesion is going to happen on this face and along these outside edges of the substrate.
All right, so the next question is, do you need to wait for the substrate to cool before starting the overmold?
I don't think you have to wait. As we run parts here, we generally don't have the substrate mold sitting right next to the overmold. So the substrate parts will be run, set aside and lined up to run in the overmold itself. So if it's a certain situation where we're asked to try to run them back to back, we can do that. It shouldn't pose too much of an issue. Like I said, it really comes down to maintaining a very tight fit of that substrate plastic into the overmold itself.
Right, so I think you started to then answer the next question. Would the traditional way of overmolding this type of part consist of the molder building 2 molds to make this part?
Yes.
Okay. The next question is venting usually an issue with overmolding?
That's in general, no. You always, depending on the material, there's always a situation where gas can be trapped. It really is specific to a certain type of feature, to a certain type of part. But no, it's not. Overmolding is not something that we have a lot of issues with venting, with gas traps.
And then the next question is similar to one that had already been asked, but you might have another look at it. Is the overmold done in a separate mold or with different hand load parts in the same mold?
In general, we make a completely separate overmold tool. That's basically a 1-to-1 of the substrate plastic. And then the specific overmold features are in that overmold tool. So it is a separate tooling. We don't add a whole new internal system and use the same base, for instance.
Right.
So we had another question that came in just before you started on this part, and it's related to the previous 2 samples. And the question is, can you make the parting line? Can you make the parting line on the bottom of the snap edge? Is it advisable?
In previous 2 sample, is that part number 2?
So just on the clip features themselves?
Yeah, just the clip features themselves, it looks like.
What is that on part 2?
Would
or
it was the
maybe 3
over this.
Yeah.
Yeah.
I'm not sure how to make the parting line.
You can kind of see where the 2 clips are. You have the back side of one of them showing there and then the front of the other. As far as where the parting line is, we kind of, if you can see down at the bottom there, you can see how the parting line jogs between each clip, little angle there. That's basically where the parting line is going to be on that. The snap feature is actually in the steel. Where I think
you can see a step parting line.
Yeah. I think what they're asking is having the parting line at the functional end of the clip itself, the sharp flat edge. And you see that.
He says yes. Can the parting line be at the bottom of the snap base?
Which is where it's kind of the opposite here. That's embedded into the other hand load. In a different situation, yes, the parting line could be there with a separate piece pulling out a hand load, for instance. In this particular instance, on this part, that clip feature is in the other hand load, the other half. The split line is on the back side of that, where you're seeing that rectangular feature.
Okay. Pop back over here. So part number 5, this one actually has a embedded copper tube. This was for a welder. So the insert's kind of floating in the sense, and once we look at the tool, kind of talk about that. Just how we position and hold that insert while we're overmolding. This is part 5. So let me shut the part off. Probably be easier to see. Got the part with shrink still in there. So that gray piece that's in there now is what the customer provided us. And then let me just do that. So you can kind of see how we're holding that copper tube in place. We went a little longer than usual. Typically, we'd only have to go with, so far in to just create a nice tight shutoff on the end here, but we had to worry about, if we did that, it's going to allow this copper tube, while the tool is filling, to move up and down within the tool and not be centered within the part. So by us making this longer on each end, it's going to prevent this tube from being able to move around. So we get a nice even wall thickness around that copper tube after molding.
Exactly. I mean, under injection pressure, you've got a lot going in there, and that piece can flex, whether it's copper or whatever it is. So the more bearing we have on the inside there, the more rigid that piece is going to be. And again, with many customer supplied substrate inserts, it's critical that they're exact every time. We've had situations in the past where substrate pieces came in and there was a variance in the arc, in the bend, in the diameter, in the length. They have to be very consistent in order for that tool to function properly every single shot.
All right, any questions on this one?
Yes, one just came in. What tolerances do you recommend for substrates?
Glenn, you'd probably be better suited for that one.
Well, as far as tolerance goes, I mean, it depends on what we're talking about. If it's say for this part, if it's the position of the tube diameter to the rest of the part, our machining tolerance for our tools themselves are plus or minus 5 thousandths, which we generally maintain well inside of that. But as far as tolerancing for the customer's parts, it's difficult for us to say we can hit plus or minus 2 thousandths. It's really dependent on the part itself and the functionality of it.
And it's really going to depend on the substrate too. In this case, we're dealing with a machined part. For us, the OD of the tube really doesn't matter. It's more where we're getting the shutoff between the tool and the insert. So obviously this face here. So if this part was too short, we'd have loose, open space here, which is going to lead to flashing. If it's too big, it's not going to fit into the tool. But like I said, the OD doesn't matter. We're just filling plastic around it. The ID somewhat too. So if that's a little loose, wherever plastic can find a space, it'll fill it.
So guys, we've got a few questions about this. The first one, are there materials that cannot be used for substrates? And would that answer be based on temperature stability?
Yes. Obviously, even things like circuit boards, anything, that circuit boards you typically don't do with high pressure injection molding. It's either low pressure or some other form. But if we're just speaking materials, anything like thin, even if it's steel or stainless steel, but it's super thin, that may not hold up under pressure. So pressure and temperature.
Okay, thanks, John. And the next question, due to the complexity of the parts, what steps do you take to limit the core cavity modifications or adjust needed after the tool is completed?
Well, I mean, we can, a lot of times what we try to do is machine things to the upper end with a little stock, a couple of thou to help our team fit them well, because ultimately we have to go in and fit the two yellow hand loads. Those are fit in there by hand just to make sure they're nice and snug. So I mean, as far as as a tolerance goes for that, I mean, we just have to make it work, and sometimes it does require maybe a little in and out of the press to make sure we have it right. But that's what we do, so that's how we proceed with that.
Okay. We've got a few minutes left. I think we'd be able to, well, this one's pretty straightforward here. It was a 2-cavity, some more clip features, but we'll skip over that one for now. If we have time, we'll come back to it. This one's a little bit more complex. This tool's got multiple shut-off surfaces, multiple actions, some reverse draft or, clip features on the inside that the customer needed for assembly. This is part of a fuel filter. So let's pull this one up and talk about it. So it looks complicated. There it is. But when you really break it down, it only ended up being 2 actions, 2 pulls from each end here. We had to work with the customer on, line of draw, making sure everything's, pulling the right way, and we can capture all these great features, so to speak. Let me shut this off here so you can kind of see. So essentially what happens, you can see these features are kind of angled in towards the center of the part, so thus creating somewhat of an undercut. So what we did to combat that was almost put a small ramp here within the tool. So as we're pulling this hand load out, or this loose piece out, this clip feature actually go up the ramp, thus releasing the hand load, and then snap back down. We ended up with 2 gates just in order to get this thing to fill. Because it really didn't have...
If that would have been a solid piece, we possibly could have filled it with 1 gate, but with the structure of that part, we needed to fill it from multiple locations. And those little clips, they did, due to the type of material that was chosen, those little clip features did flex out of position and then popped right back to where the customer needed them.
Yep. Any other questions on this one, or?
John, there's one, but it says on the first part, how is the little hand load plug removed?
Little hand load on the previous part?
You know what? I'm not certain. He says on the first part.
Oh, possibly the round feature with the 3 internal clips.
Yeah, well, he says he does say part 1, so he's asking on the first part, or on part 1, I guess, the one from the beginning. It still appears die locked. How is the little hand load plug removed?
Well, so basically that hand load is 2 pieces. The magenta one that he just pulled free, that pops this direction. And then that other piece, if I'm right, John, that other piece just pulls back.
Yeah, I'm trying to remember how it does appear die locked. I don't know why, but I'm trying to remember what we did, because this screw is actually threaded into this hand piece. So I mean, I'm trying to remember if that was broken up.
It doesn't look like it's split, but it may have been.
Yeah.
It may have been.
Yeah, there's a reason for this threaded, and this was to pull it out. You know what? This might be I think this popped in to spread the clips in order to pull this out. That's what this was for. This was actually a tool it got inserted into there to spread the clips out, and then this pushed out.
Yeah,
the tool's a few years old. Yeah, it's been a while.
Yeah, that's more of a tool to flex those clips outward so they can be extracted.
Yeah, because this is going through there. Okay.
So,
Good catch.
Next question, does Eccentric make the tools by themselves or through a specialized tool maker? And then if yes, which the answer is yes, we make tools in-house. Then how do you capture all the requirements of the client and by the tool maker DFM point of view?
I mean, that's all done on the front end with one of our application engineers, just understanding the project and what the expectations are of the project. We deal with so many customers at many different times in the product development process, from I just need 25 pieces to prove out my design in a specific grade of material because I can't do it with 3D printing, or need to bridge gap to my production tool being made in China that's taking longer than I anticipated. So it's just really talking on the front end and doing the discovery and matching up the expectations between us and you, the customer.
And obviously, when our design team gets these part files in and starts building around it for the tooling, if they see anything that wasn't caught on the initial DFM, an undercut, zero draft issue, whatever it is, we'll go back to the customer, explain the situation, provide potential options, suggestions. Same goes for thick-walled parts. We'll suggest coring certain features out, things like that. Try to make sure we hit anything that may be an issue on down the road before it actually becomes a problem.
The next two questions are similar. How long do you have to cool the part so the snaps are responsive? And likewise, how do you control warping of those clips? Do you have to wait until it's cooled, or do you remove the part slowly?
You basically demold those clips immediately while the part is still, quote, warm. And depending on the material, some materials snap back really well. Other materials aren't made for that. It comes down to material choice. You don't want a hard polycarb material or something like that in certain situations. So yeah, we would pull that out of there immediately. That wouldn't sit on the table. That would basically set the part on the tool.
Okay. Next question, does Eccentric require customers to include draft details in our models, or can Eccentric add those details? And do other injection molding companies generally work the same way?
We generally, the part file we get, like I said before, everything should be properly drafted for the proper pull direction. In most cases, those are designed well, but we do it at some point on certain parts, certain projects. We will go back to the customer and suggest, if I could get another half-degree draft here or a little change here, that would really improve the functionality of the tool and not affect the actual performance of the part itself as it was intended.
Mm-hmm.
All right. Next question. Can you provide any insight on designing parts with a living hinge incorporated into the design? On that note, are you capable of coining a surface to produce a hinge? And I believe, guys, the parts clinic you did in June, I think one of the parts actually had a hinge, didn't it?
Yes.
I believe so.
Yes.
All right, so I'll let you guys go ahead and answer that, but I wanted to let our listeners know that if you go to our website, you'll be able to watch the video of the summer parts clinic, and you'll be able to see a little bit more about that living hinge. Go ahead.
Yeah, I mean, if you have a part has a clamshell feature, whatever it is, a soap dish container, whatever it is, it really comes down to the design they want. Generally, a living hinge has an arced feature to it. It's thinner material, so it flexes. The material choice is critical. Of course, you don't want that to crack and break, so there needs to be some amount of flexibility in the plastic, but it generally is a thinner wall and has a round feature on it. So when those are clamshelled together, that all comes back together. But it really is specific to the project and the material you're needing.
We have one last question, guys. Does Eccentric have the capability to mold larger parts requiring 1,500 tonnage presses or larger?
Not at this time. Yeah, our largest footprint we can do is roughly a 24-inch by 24-inch by 5-inch part, or roughly a 28-ounce shot size.
It looks like that's the last question, guys. So thank you very much. Thanks everyone for attending today. Again, we encourage you to follow Eccentric Mold and Engineering on LinkedIn so that you can stay up to date on our latest blog topics and our webinar schedules. We will send a link to this recording within 3 business days. And if you have any questions about today's topic, please feel free to email us. You can email us at sales@eccentricmold.com or info@eccentricmold.com. And likewise, if you have a project that you want to get started, the address there, my.eccentricmold.com/quote hashtag is the way to get to it, or go to our website and click on start a project or get a quote. Thanks, and have a great day and a wonderful end of your week. Bye, everybody.
Thank you, everyone.
Thanks a lot, everybody.